Hello there. This lecture is all about frequency distributions. So remember, descriptive statistics are a set of mathematical procedures for organizing, summarizing, and simplifying data. Well, often, many variables are measured for many participants, and the data is unmanageable. So you just have tons and tons of data, and it's hard to make sense of it. So today, this lecture is going to cover the simplest way to describe data, which is a frequency distribution. And a frequency distribution involves simply counting the number of each score or response, or participants, within each category to determine the proportion of participants corresponding to each score, response, or category. So to break down the term frequency distributions, frequency, the number of people with a particular score. Distribution, the spread of those scores based on the range of scores and the frequency of each. So this lecture is going to cover more in depth of what the purpose of a frequency distribution is, then a little bit of background information on statistical notation, so what certain symbols mean so that the rest of the lecture will make sense, and then some steps for how to create a full frequency distribution table, then how to interpret that frequency distribution table, so how to look at that table and understand the data better, and then how to use that table to calculate values. So sometimes it's easier not only to view the trends in your data by putting the data into a table, but also to do calculations when you have a large amount of data. Then I'm going to get into something called a grouped frequency distribution table, which is a special frequency distribution table that you use when you have a really large range of scores. Then frequency distribution graphs, so how you take the information from the table and put it into a nice pretty picture. And then the shapes of those frequency distribution graphs. And shapes of frequency distribution graphs will be really important for the lecture and the content of the chapter on measures of central tendency, because you have to know the shape of the distribution to identify appropriate measures of central tendency. So as you've been warned, statistics is cumulative. Everything builds upon the previous material. So it's important that you understand the previous lecture to understand this lecture, and it's important that you understand this lecture to understand subsequent lectures. Okay, so first things first, what is the purpose of a frequency distribution? Well, the frequency distribution table will provide a clearer picture of the trends in your data versus mass amounts of disorganized data. So you can answer questions like, do scores tend to be high, low, or in the middle? Are scores clustered together or spread out among possible scores? Or in other words, how much variability is in my distribution? You can also see how a single score compares to the entire distribution of scores. So for instance, among the distribution of employees at Winco, what percentile is someone with a performance review score of 6 on a scale of 1 to 10? Those kinds of questions can be answered by putting your data into a frequency distribution table or a frequency distribution graph for that matter. Also, like I mentioned before, you can use frequency distribution tables to simplify calculations. So in a full frequency distribution table, you will be calculating the probability or proportion. Those two terms can be used synonymously with each other. Percentages and percentiles. And I'll break down what all three of those P's mean here in a minute. Then you can also simplify calculations that you need to do for measures of central tendency and variability. So by putting your numbers into tables, you can prevent mistakes and make calculations much easier compared to trying to manipulate 100 numbers that are just spread out all over the place and not placed into any organized fashion. So before I get into all of the fun stuff about frequency distribution tables and graphs and calculations, it's important that you understand the statistical notation associated with these things. So whenever you see X, X is just the statistical notation for a single score. So whenever you measure a variable, for instance, number of cups of coffee or GPA or anything you want to measure, you're going to have many, many scores associated with each person that you're measuring. And each one of those scores is referred to as an X value. Now, F represents F for frequency, frequency of a score. How often does that particular score appear in my data set? Now, uppercase N, that represents the population size. So in the previous lecture, you learned about the difference between a population and a sample. A population is everybody that you're interested in. And oftentimes, we don't have access to the population. So for instance, I'm an industrial organizational psychologist. So in most of my studies, my population of interest are employees. Well, guess what? Probably not going to have access to every employee in the whole world or even in the country. So I take a subset of those employees, a sample, and study those as a proxy for the population. So whenever you're working with a sample, the sample size is denoted by a lowercase n. You can just think about it this way. Uppercase N, it's the bigger N, bigger size, bigger population, everybody you're interested in. And then the small version of that, the sample, the subset of the population, is the smaller, the lowercase n. I don't know if that helps, but there you go. Now this funky little squiggle thing that's next right here, sigma, this represents the sum or addition. So you're probably used to seeing summation with plus signs. But in statistics, we are typically manipulating a whole set of data. So it's a lot easier to perform calculations with that data in separate columns, as you'll see in a little bit, and then you sum down. So summation is just used to combine scores or to perform mathematical operations with scores, and then you combine them at the end. So just going back to the order of operations, you should be able to understand why these notations represent these specific instructions for manipulating data. I'm not going to go through each one of those. If you don't understand any of these, please feel free to ask your professor for assistance in understanding it, and then review some algebraic principles and the order of operations. And I'll give you some examples of how to calculate the sum of x and sum of x squared in a little while when I get into performing calculations with frequency distribution tables. So some steps for creating this full frequency distribution table for a single variable. So how many times did each phlebotomist at Quest Diagnostics on Green Valley Parkway have a missed stick for a blood draw this week? Well, real quick, what do you guys think? Are we working with a sample or a population? Let's say I'm the manager at Quest Diagnostics, and this is the group of people that I am interested in, these phlebotomists that work for me. Sample or population? Well, hopefully you identified this as a population. This is a situation, and often this happens in the workplace, where you do have access to everybody that you care about. If I'm the manager at Quest Diagnostics, the only people I care about are my employees. So this represents a population of data. Now, if I'm going to break down this raw data, this is a pretty simple set of data. There's not a whole lot of range, and there's not a whole lot of values in my data set or scores in my data set. But you can still see how it can just be kind of a jumble and confusing. So, for instance, just to break this down, this 2 represents 2 missed sticks for a blood draw for one of the phlebotomists. So each number represents one phlebotomist. This person had 0 missed sticks. Another 0, another 0. This phlebotomist had 4 missed sticks for a blood draw this week. So you'll see how this raw data translates into a table form. So the first step for creating a full frequency distribution table, and I keep calling it a full frequency distribution table because it includes all of the descriptions of the data, all of the little pieces of information. Now, sometimes when you're using a frequency distribution table for calculation purposes, you'll only include these 2 columns to start, and then you'll do your calculations. You won't have the p, the percent, and the percentile. All right. Back to creating a full frequency distribution table. So the first step, you want to create a table with 5 columns. So the first column represents the variable, so you'll have all the scores here, the full range of scores. We'll get to that in a second. This represents the frequency of each score. This represents the proportion or the probability associated with each score, the percentage, and then the percentile. So the first thing you want to do is just kind of outline your table to get prepared to fill it all in. Step 2. Now you want to create a row beneath the X, or the variable name column. So sometimes you'll see this labeled as X. In your textbook, a lot of the frequency distribution tables just have an X here. Remember, X just represents scores. I like to put the variable name here because it helps in identifying what's actually being measured. Now, one thing I want to mention is that you want to have the full range of scores represented here, from top to bottom, highest to lowest. See this little do not skip values? I put that there because sometimes, like for instance, let's say that we had a 7 in this data set. Well, we don't have a 5 or a 6, but you would still want to include those in this table because you want the full range of values from the highest to the lowest. So if we look at this data set, I can quickly see that the lowest score is a 0 and the highest score is a 4. So the minimum number of missed sticks for a blood draw was 0 in my population, and the most that any phlebotomist had was 4. So that full range is represented right here. Lowest, highest, bottom, top. Or highest to lowest, top to bottom, however you want to think about it. So that's the first step, represent the full range of values. Okay, so the next step, you want to fill out that F column, the frequency column. So you want to look and you want to count how many times does each score appear in my data set. So for instance, looking up here, how many times do I see a 4 in this data? Well, let's see. 1, 2, 3 of them. So guess what? In the frequency column, you're going to put a 3 there. There's 3 4s in my data set. Or in other words, there are 3 phlebotomists in this population who missed 4 sticks last week. Conversely, there are 7 phlebotomists in this population who had 2 missed sticks last week. So just simplifying that information. And you can already start to see that by putting your information in this format, it makes it a lot clearer than just looking at a bunch of numbers. All right, so now we are ready to fill in this P column. P stands for proportion or probability. Again, those two terms are pretty much used synonymously with each other, just depending on the purpose of how you want to explain your data. And the way that you find the p-value, or the proportion or probability, is to take the frequency, or how many times a particular score appears in your data set, divided by the sample or population size, depending on what you're working with here. So, how many times, for instance, does 4 appear in my data set? Or in other words, how many phlebotomists had 4 missed sticks this week? Well, 3 did. So 3 would be the F in this case. So F divided by the total number of scores in my data set, or in other words, my sample or my population size. In this case, population size. Well, the way that you find that, you can just add your frequencies together. So we have 3 plus 2 plus 7 plus 2 plus 37 gives you a total of 51 phlebotomists in this population. Now you could also get that by just adding how many scores you have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't feel like counting all that. I'm just going to go ahead and add my F's and I'm good to go. I know there's 51. You could also find that. Again, you'd find 51 if you looked at how many scores are there. So 3 out of 51 phlebotomists had 4 missed sticks for a blood draw this week. And 3 divided by 51 gives you 0.059. So you could state this in 2 ways. You could say the proportion of phlebotomists with 4 missed sticks this week is 0.059. So another way that you could state this is in terms of probability. So you could say the probability, if I were to just randomly select a phlebotomist from Quest Diagnostics on Green Valley, how likely would it be that they had 4 missed sticks for blood draws this week? Well, the probability of randomly selecting a phlebotomist with 4 missed sticks this week is 0.059. The number is the same, but the interpretation is somewhat different. Next, you want to fill out the percent column. Now, the percent column is pretty simple to calculate. You're just taking that proportion or probability and you're multiplying it by 100. I don't know about you, but I prefer to describe things in terms of percentages instead of probabilities or proportions. It's just something we're all more familiar with. So if you look at this first column, or this first row here, the 4 missed sticks, 0.059 p-value multiplied by 100, you'll see that up here, gives you 5.9%, and you can just say 5.9% of phlebotomists missed 4 sticks on a blood draw this week. Now, that's kind of related to the proportion version of the p-value here. You could also state it in terms more of a probability. You could say, going back to here, there is a 5.9% chance of randomly selecting a phlebotomist with 4 missed sticks this week, if you wanted to put it in terms of that. Either way is fine. Now, the next column is somewhat complicated to compute. The math is pretty simple, but people do get tripped up quite often on doing this calculation. And I tried to simplify it as much as I could, putting this up here. So you're going to find the percentile rank, or the percentile. Another way to state this is the cumulative percent. And the way that you find that is you start at the percentage for the lowest score. Then you add that percentage to the next highest, the percentage for the next highest score. And that gives you a percentile. Then you take that percentile, add it, so you'll see here, we started with 72.5, the percentage for the lowest score, 0. Add that to the percentage for the next highest score, so 72.5 plus 3.9, that gives you 76.4. Then you add that percentile to the percentage for the next highest score, so 76.4, boom, plus 13.6 right there, or sorry, 13.7 right there, 90.1. And you just keep moving on up. 90.1 plus 3.9 equals 94. 94, boom, plus 5.9, there it is, 99.9. So what we could say here, and what percentile tells you, is it tells you the percentage of scores that are less than or equal to any given score in your data set that you're interested in. So for example, if we look at this one right here, this would tell us that a phlebotomist with 4 missed sticks is at the 99.9th percentile. Or in other words, 99.9% of phlebotomists missed 4 or fewer sticks this week. Now, one thing that I really want to point out is that sometimes there's rounding error when we're doing this. So if you look at this, one way to check your calculations would be to make sure that 100% of your population or sample is represented by this table. So if you add up all these percentages, you should get something pretty close to 100 within rounding error. That's one way that you can check your work to make sure that you did your percentages and your probabilities correctly. So add all these together, you get 99.9, pretty darn close to 100. It's within rounding error. Now another way that you could check your work for your percentiles, remember that's the one that people tend to mess up on. Make sure that once you get up to the highest score in your data set, that percentile is equal to the sum of your percentages. Pretty close to 100 is what it'll always be, but it's nice to check and make sure that the rounding error is the same. That's a good sign that you did your math correctly. So if you think about rounding error and we go back here, it makes sense. Technically, this is pretty much everyone within rounding error, so you could say that, in other words, all of the phlebotomists, 100%, missed 4 or fewer sticks this week, which makes sense if you look at the data. So this is just a summary of the steps that I just went through with you, just for your own, your own notes, just to have it in one place instead of on a bunch of different slides. Okay. So one thing that I want to point out is that whenever you're creating a full frequency distribution table to present maybe in a PowerPoint for a group of people who are interested in the data, or maybe you're drafting a paper for your research methods class, or maybe you're an advanced student and you are submitting something for publication, you don't want to show your calculations. That may be something silly to point out, but I just want you guys to know that I showed my calculations just so you would know where my numbers are coming from. This is really just to illustrate the calculations. But in reality, when you present these things, you don't include the calculations, you just include the values. So when you look at this, it's nice and pretty. You can see the trends in the data. You can see, oh wow, there's a lot of people with 2 missed sticks. But then you get down here and you're like, wow, we've got some good phlebotomists. Most people didn't miss any sticks on a blood draw last or this week. And then you can look at the proportions or proportions or probabilities, percentages, and then the percentiles. And if you think about percentile, remember percentile represents the percentage that have a score that's less than or equal to a particular score. It makes sense that once you start moving up to higher scores, it's increasing. So for instance, 72.5% of this population have a score of 0 or less. Well, there's nothing less than 0, so it makes sense that that's equal to the percentage of people that have 0. Then up here, 76.4% of the population had 1 or fewer missed sticks for a blood draw, and so on and so forth. Okay, so interpreting these values. So remember, it's all about making your data useful, being able to look at your data and answer questions with it. Frequency distribution tables are great for that. So we already figured out how to find the population or the sample size. You add up all the frequencies here. So how many phlebotomists are in the population? Add those up. There's 51 of them. Another question you could ask about the data, how many phlebotomists had more than 2 missed sticks? Well, instead of looking at raw data and trying to count that up, you can simply say, okay, let me look at my table. Well, more than 2 would be, in this case, 3 or 4. Well, I had 2 phlebotomists who missed 3, 3 phlebotomists who missed 4, 2 plus 3 is 5. So 5 missed more than 2 sticks. What percentile is a phlebotomist with 3 missed sticks on a blood draw this week? Well, you could say, real quickly, let me find 3. Remember, we're looking at the score of 3. So this column here, 3, pertains to the 94th percentile. So this means that 94% of phlebotomists had 3 or fewer missed sticks on a blood draw. Or they're at the 94th percentile. You could also say, what percentage of phlebotomists had 2 or fewer missed sticks? Well, remember, a score or fewer, if you're looking at 2 or fewer, you're looking at a percentile for the score of 2. So you could go straight to, okay, 2, there it is, 90.1 percentile. So 90.1% of phlebotomists had 2 or fewer missed sticks. But if you're still not real comfortable with what does percentile mean, you could just go back to your frequencies and say, okay, 2 or fewer. 2 or fewer here. 7 had 2, 2 had 1, 37 had 0. 7 plus 2 plus 37 means that 46 phlebotomists had 2 or fewer missed sticks. What percentage of the population is that? 46 divided by the population size of 51, 90.1%. Check it out. Same as the percentile. Here is another example of maybe a practical use for this data. So let's say I'm the manager and I really want to have some quality control for my phlebotomist. So I decide that, you know what, if you are in the 90th percentile or higher for missed sticks on a blood draw, that's unacceptable, and I'm just going to fire you outright. It's not acceptable. So how many phlebotomists would be fired? So you can go here and you could say, okay, 90th percentile or higher. Basically meaning that I want to fire people who have missed sticks in the top 10%. Want to keep the people who have missed sticks in the bottom 90%. That's another way you could think about it. Well, how many have that? Okay. Well, 7 at the 90.1 percentile, that's higher than 90 percentile. 2 at the 94th percentile, 3 at the 99.9th percentile. 3 plus 2 plus 7, 12 phlebotomists would be fired. Now I want you to stop for a second and think about this strategy. What is inherently wrong with this strategy? If I was going to say, I'm going to fire you if you're at the 90th percentile or higher. Think about it. How would you feel if you were in the 90th percentile or higher? What kind of questions would you have for this strategy? Well, think about it. In this particular study, there's no control for the number of patients that person saw that week. So let's say that one of these people who had 0 missed sticks on a blood draw saw 5 patients this week. And this person up here who had 4, one of these people who had 4 missed sticks, saw 50 patients. Well, guess what? You're probably going to have more missed sticks on a blood draw if you're seeing more patients in the first place. So just want to point out that you need to be a critical consumer of research. Always think about what the implications of your data collection strategy are before you start to make decisions based on that data. Okay, now I want to switch gears into calculating values with a frequency distribution table. So you'll see that the only thing that I kept from the original frequency distribution table are the missed sticks, so the scores in this data set, and then the frequency of each. I'm not going to keep my P, my percent, and my percentile for the calculations that I'm going to be doing here in a minute. So pretend that these don't exist yet, and that you'll create those when you have to answer specific types of questions. So you'll notice as I go through this that whenever you have a mathematical operation other than summation that needs to take place, you can do that in columns, and then when you're finished doing those mathematical operations, you can sum it all together to get your sum there. I'll walk you through that in here in just a second. So one thing that's really important that students forget quite often is that when you're using a frequency distribution table to find the sum of x, or the total sum of all the scores in your data set, you cannot simply add up the values that are here. You can't say, oh, 4 plus 3 plus 2 plus 1 plus 0. That's not going to give you the sum of all the scores because you won't be taking into account how often those scores appeared in your data set or the frequency of each score. So if you look at it in raw data form, you can't just add 1, 2 to 1, 4 to 1, 3 to 1, 1 because again, that doesn't capture how often you see that in your data set. So you have to take that into account. So to do that in a frequency distribution table format, you need to take each score, multiply it by its respective frequency, and then add those together. So whenever you see sum of x, you could also think about it if you're looking at a frequency distribution table as the sum of fx. So x times f, or f times x, however you want to do it, you're going to get the same number. Over here, add it together. So 4 times 3 is 12. 3 phlebotomists had 4 missed sticks for a total of 12 missed sticks among those 3 phlebotomists, for example. 3 times 2 is 6. 2 times 7 is 14. 1 times 2 is 2. 0 times 37 is 0. Add all those together and you get 34. So there were 34 missed sticks in total this week among all the phlebotomists at Quest Diagnostics, for example. Now that's the same value that you would get if you were looking at your raw data and you wanted to add all those together. You would get 34 as well. If you have a lot of data and there's not a whole lot of zeros involved, that's going to be ugly and not very fun and very easy to make mistakes. So if you can get comfortable with this strategy, it will help you in the future. Keeps things organized and more simple and less chance of making an error. So 34 missed sticks this week. I tried to color code things to make it easier to understand. See this nice red box corresponding to the red text here. This is all we care about. Well, what if I asked you, what's the average or the mean? In statistics, we call the average the mean. Not because we're mean and angry, but that's just the statistical term for it. So what is the average or the mean missed sticks in this population? Well, you'll see a lot of this in the central tendency lecture, but just as a little preview, the formula for the mean is the sum of x divided by n. Or in other words, the total sum of all the scores, in this case in the population, divided by how many scores are in the population. Well, we already found the sum of x. We know that if we take all of those missed sticks for all of the phlebotomists, we add them together, we get 34. Divide that by the total population size. Talked about this earlier, 51. Add up all the frequencies. How many phlebotomists are in this population? 51. You get 0.667. So you can see my green numbers here corresponding to where I got that information. Add all these together to get 51, my denominator. Add all these together to get 34. Total sum of missed sticks, my numerator for the mean. Another calculation that you may need to do in preparation for something that is called the sum of squared deviations. You'll get to that in variability. Not quite yet, but just to get you ready for some of the calculations you'll be doing there. What if you need to find the sum of x squared? Or the sum of all squared scores? Well, if you think about the order of operations, you need to first solve for your exponent, and then you need to do some summation. So the first step that you want to do, again, solve for the exponent, you need to square each x. So these represent x values right here. So 4 times 4 is 16. 3 times 3 is 9. 2 times 2 is 4. 1 times 1, 1. 0 times 0 is 0. Squaring each score in your data set. Now, just like you couldn't just say, oh, 4 plus 3 plus 2 plus 1 gives me the sum of all the scores. You cannot add 16 plus 9 plus 4 plus 1 and get the sum of all squared scores. Just like before, you need to take those frequencies into account. So you need to multiply the frequencies by the x squared values. So 3 times 16 gives you 48. 2 times 9 gives you 18. 7 times 4, 28. 2 times 1, 2. 37 times 0 is 0. Add those together and you get 96 for the sum of all squared scores. Now you could use the raw data. Here I showed you how to do it for the mean, but here you could literally square every score in your data set, add those bad boys together, you're going to get the same answer. But I certainly prefer this method, and you will too if you have a large amount of data. If you're given a manageable amount of data and you want to do it this way, that's perfectly okay. So let's move on to grouped frequency distribution tables. So remember, the whole point of frequency distribution tables is to simplify large amounts of data. Well, sometimes when there's a wide range in scores in your data set, so for instance, age and years, sometimes you might have, if you're looking at age, you might have people ranging in age from 18 to 100. Well, you're not going to want to have a row to represent every single age from 18 to 100. It's not really going to simplify your data very much. It's going to be pretty chaotic and hard to read. So a traditional frequency distribution table, when you list each value for each variable, the full range, that's not going to work out. So it's not really efficient. So when you have a large range of x values, you want to use a grouped frequency distribution table instead. So as opposed to listing each individual score, you're going to break those scores into intervals or groups. So for instance, instead of having a row for 20, 21, 22, 23, 24, 25, 26, 27, 28, and 29, you could just have one group that's from 20 to 29, for instance. Now there is a specific process that you want to go through to make a frequency distribution or group frequency distribution table that is narrow enough to provide rich information about your data, but broad enough so that you don't have an overwhelming amount of rows in your table. So the way that you can group scores together, and this is not in your book, but this is a strategy that will really help you figure it out pretty easily without trying to create a bunch of different tables to see which one's better. The first step is to figure out how many groups do I think I need to have in my table. And the way that you can do that is you can use the 2k greater than or equal to n or n, depending on you're working with a sample or population rule. And basically, you try to find an exponent of 2 that gives you a final value that's greater than or equal to the number of scores in your data set. And then whatever that exponent is, this little k, that'll tell you how many groups you need to have. And I'll show you an example of that here in just a second. Then once you figure out what the heck is k, how many groups should I strive for in my grouped frequency distribution table, you can figure out the width that will get you to that number of groups. So how much width should I have for each of my different groups? How many scores should be covered for each group, in other words? Now you want, again, the purpose is to simplify information. So you want your group width to be an easy to understand number. And in general, any multiple of 2, 5, or 10 is pretty easy to understand, easy for whoever's looking at your table to know how wide your width is. Then, to figure out what the width is actually going to be, you need to take your largest value in your data set, subtract your smallest value in your data set, so your largest score minus your smallest score, and divide that by k, or that number that you found up here, the approximate number of groups. Now, if you get an ugly number for this, you want to round that to a multiple of 2, 5, or 10 to make it nice and pretty and easy to understand. Now, there's a couple of rules that you must follow when you're doing this. When you're constructing this, after you've figured out the width of your groups, you want to make sure that the lowest score in each group is a multiple of the width, because you want to make it easy to identify for whoever's looking at your table what is the width of your groups. How many scores are encompassed in each group? Now you also, when you create your grouped frequency distribution table, you want to make sure that each group is the same width. You want to make sure that there are no duplicates of scores for each group, so mutually exclusive groups, no overlap. And you want to make sure that you cover the full range of scores in your data set, so all inclusive. So just like a standard frequency distribution table, you want to represent the full range of values. But in the grouped frequency distribution table, you're just breaking those up into groups, but you still want to represent the full range of scores in your data set. So here is an example. Let's say, we're keeping it medical today with these examples. Let's say you're a nurse at a hospital and there's a new outbreak of something really nasty that's happening. And you are starting to kind of notice a trend in the data of maybe there's some people who are a certain age who are coming in, but you want to graph this out and put it into a table. So you collect some data from the first 20 patients who come in with this disease, and you want to know if the person's age maybe is related to how susceptible they are to the disease. So your raw data is right here below, just this jumble of numbers. Now, if you're looking at this, I can identify 18 as the youngest person in my sample, right? This is a sample now because there's more than 20 patients. This is just the group that we're working with, but we're interested in all patients. So 18 is my lowest score, or no, wait, 16. Yeah, 16 is my youngest. And then the oldest person in this sample is 53. That's a lot of rows in a frequency distribution table. If we're trying to cover every value between 16 and 53, that is not going to be pretty, and it's not really going to be that useful. We'll have a lot of zeros in that table, in other words, for frequencies. So let's go ahead and create a grouped frequency distribution table with this data. Remember, the first step is to figure out how many groups approximately should we have using the 2k greater than or equal to n rule. See, I have a lowercase n here because I'm working with the sample. So if my sample size is 20, 1, 2, 3, 4, 5, 6, 7, 8, 20 scores here. You also see there's 20 patients. What is k? So in other words, what exponent of 2 will give me a value that's greater than or equal to 20 in this case? Well, I don't know right off the top of my head, so I went through and I just started plugging in numbers. So I started with 2. So the square version of 2, 2 squared. That's 4. That's not going to cut it. That's not greater than or equal to my sample size of 20. 2 to the third power. 2 times 2 is 4. 4 times 2 is 8. That's not going to get me a number that's greater than or equal to my sample size of 20. 2 to the fourth power gives you 16. Still not greater than or equal to 20. Finally, when I put 5 in for k, for my exponent, 2 to the fifth power is 32, and I'm done. I figured out that is greater than or equal to my sample size. K is equal to 5. So to have an accurate and, well, not really accurate, maybe optimal number of groups would be 5. Enough groups so that you have adequate information, but not so many that it's overwhelming and not simple. Next step. So if I'm going to have 5 groups, what does my group width need to be? Well, the largest value in my data set, the oldest person, identified as 53. The youngest person, or the smallest score in my data set, is 16. So I take my largest minus my smallest, or 53 minus 16, divide it by that k that I just found of 5. Well, guess what? When I take 53 minus 16. That gives me 37. Divide that by k, which is 5, 7.4. That's an ugly number. I do not want to have that as my group width. It's not going to simplify anything. Well, remember, we always strive to have multiples of 2, 5, or 10. I'm going to go ahead and make this 10. Just round right on up. My group width is going to be 10. Okay, so we figured out our group width. We know what our highest and our lowest score is in our data set. We're ready to create the grouped frequency distribution table. So remember, rule 3, the lowest score in each group should be a multiple of the width. In this case, that's 10. And if I think about my highest and my lowest score, then I want to make sure that I capture all ages between 53 and 16. And you'll see that I did that here. But we're going to start with the lowest score in each group, multiple of 10. So I'm going to start with, again, just like the other frequency distribution table, you go from highest to lowest, top to bottom, or lowest to highest, bottom to top, however you want to do it. I'm going to go ahead and start with 10. And I know that that's going to capture my 16. And I'm going to work my way up all the way to 50 because I know that that's going to capture the 53. So 10, 20, 30, 40, 50. That's the lowest score in each group, and indeed I made it a multiple of 10 because that was the group width that I decided to choose. Then you want to make sure that the high end for each group, or the highest score in each group, is just below the lowest score for the next highest group. All right, so we have 10 to 19. 19 is just below 20. 20 to 29, 29 just below 30. 30 to 39, 39 is just below that next score. 40, 40 to 49, just below 50. And then 50 to 59. Again, I captured 16 through 53 here. 16 falls here, 53 falls here. So you want to make sure, again, that your groups are mutually exclusive and all-inclusive. I've already covered all-inclusive. We've got the full range of scores represented here. Mutually exclusive meaning that there's nobody in our data set who falls into multiple groups. If you are in this group between 10 and 19, you are not from age 20 to 29. Similarly, if you fall in this group, I'm aged between 20 and 29, I'm not going to fall in this group, or this group. Mutually exclusive. So just like with the regular standard frequency distribution table, when you just have single scores here, when you go to fill in your F column, your frequency, you simply count how many times those particular scores are in your data set. So how many people in my data set are between the ages of 50 and 59? Well, let's see. 1 and 2, and that's it. There you go. Now check this out. Remember, before I said you had to capture the full range of scores. Well, I did here, and sometimes when you do that, you aren't going to have any scores that have a particular value. But that's okay. You just stick a 0 there. You want to capture the full range, even if there are some groups that have no scores that are in that range. Just like when you do a regular standard frequency distribution table that isn't grouped, you have the same thing. Full range of scores. Sometimes there are no scores with that particular value. You just stick a 0 in the F column. And you'll see why that's important when we get to frequency distribution graphs, which is coming up next. But before I get there, I want to point out something about grouped frequency distribution tables. Yes, they are super useful for summarizing data, especially if you have a large range of scores. But there's a problem. You lose information regarding specific values for each score. Especially if you have wider intervals, you're losing even more information. So this information loss makes it pretty much impossible to perform any calculations with the data in table form. For instance, there's no way to find the mean from a group frequency distribution because what is the sum of x? What is 50 through 59 times 2? Remember, to get the sum of x, you have to multiply across, your score times the frequency, and then add that together to get your sum of x. It's not going to happen in a group frequency distribution table. Makes no sense. So sometimes, if you're wanting to do it for calculation purposes, this isn't the way to go. But if it's simply to present the information, to describe the data, this can be optimal if you have a large range of scores in your data set. Some other examples other than age, when you'd have a large range, would be like income or how long somebody's been at their job, all sorts of things. Some people have been there for a day, some people may have been there for 40 years, who knows? So let's go ahead and move on to frequency distribution graphs. So far we've been working with tables. Now we're moving on to nice pretty pictures, and typically the frequency distribution graphs are based on the frequency distribution table. And in almost every case, you need to figure out the table before you can put it into graphical form. So in addition to making a nice pretty picture of your data, frequency distribution graphs are used to detect the shape of your distribution, which I'll talk about here in a little bit. Before we get to that, here are some basic characteristics of any frequency distribution graph. So you have the x-axis. That's the horizontal line at the bottom of the graph. And for the x-axis, you're going to label that with all the x values or all the scores in your frequency distribution table from lowest to highest, left to right, along that horizontal axis in your data set or in your graph. Then you have the y-axis. That's the vertical line at the left side of the graph. And you label the y-axis with the full range of frequencies present for the x values or the scores in your data set, from lowest to highest, bottom to top. Now, one thing I want to point out with your frequency distribution graph, it's okay to count by 2s, 5s, or 10s if there's a large range of frequencies. So like let's say that you have frequencies that go up to 100. You're not going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 100. You could have, 10, 20, 30, 40, or 5, 10, 15, 20, all the way up to 100. And that's perfectly okay. Again, it's all about simplifying your data, helping it make sense. So you want to plot your data for each score by locating the score on the x-axis and then drawing a bar from the x value or the score to the height corresponding to the appropriate frequency. So that's how you do it. And when you look at some examples, that might make more sense. Okay, so there's different types of frequency distribution graphs. So whenever you're graphing nominal and ordinal data, which typically are discrete variables, you use a bar graph. And in a bar graph, the bars do not touch each other. So just to give you a quick example of a bar graph, there's a bar graph. We'll get to that in a minute. The bars do not touch each other. So the reason that you want to graph nominal and ordinal data using the bar graph where the bars don't touch, for a nominal scale, that space between the bars emphasizes that the scale consists of separate, distinct categories. Remember, nominal data is basically just categorical. You're placing people into different categories that are completely separate from each other. Now for an ordinal scale, when you're placing things in a meaningful order, but there's not necessarily an equal distance between categories, you don't want the bars to touch in your frequency distribution graph because you cannot assume that each category is the same size. So bar graphs for nominal or ordinal data. Now, whenever you're working with interval or ratio data, which is typically a continuous variable, you want to use a histogram. Now, a histogram looks just like a bar graph, but the bars touch. So the reason that the bars touch in a histogram, and the reason you want to use a histogram for interval or ratio data, can be two ways. So if you're using interval or ratio data that's continuous, the bars touch to represent the upper and lower real limits, which capture the true intervals between response options or scores. So the bars for each x value touch halfway below and halfway above to represent those real limits. So you'll see the bars touch halfway below and halfway above in a histogram. Now, sometimes you have interval or ratio data that is not continuous. So for example, number of cars owned, number of children, number of missed sticks for a blood draw. So remember, continuous data means that there can be any interval in between whole numbers. You can have fractions of something. Whereas discrete means you're counting something, right? You're counting something, you're not going to have any fractions in between, just whole numbers. So again, you can have interval or ratio data that's not continuous if it's limited to whole number responses. You can't divide something up. So if you're thinking about number of missed sticks on a blood draw, you're not going to have 1.5 missed sticks. You either missed it or you didn't. Now you still want to use a histogram for that data because the bars touch to indicate that each category is the same size. So 1 is 1 away from 2, 2 is 1 away from 3, 3 is 1 away from 4, and so on and so forth. Now you can also use a polygon for interval and ratio data, and that's instead of drawing bars, you can draw little dots and then connect the dots. So let's go ahead and break down this bar graph that was used to display how many students in one of my past classes had each major declared. So if we're looking at the frequency distribution table, 20 students were a pre-nursing major, 1 was a nursing, 7 were psychology, 1 was biology, and so on and so forth. This is a nominal variable. Major is nominal. It's not numeric in nature. It's simply categories that we're looking at. So if you think about creating this bar graph, remember before I said that you want to place your values on the x-axis in order from lowest to highest, left to right? Well, guess what? The order that you place your categories for nominal data is completely arbitrary because there's no real order here. There's no numeric values. So you can put them in any order that you like. It doesn't really matter. Just put them right there. Each different category is represented by its own bar, and you label them along this x-axis. So if you want to look at how the graph corresponds to the table, you can see, okay, there's 20 pre-nursing majors. So here's pre-nursing on the x-axis, and the bar height corresponds to a frequency of 20. Then if I go look at sociology, here's sociology, the bar corresponds to a frequency of 1. So you can see how the table corresponds to the graph. And it's a bar graph, the bars don't touch, it's nominal data. These gaps represent that each category is separate. Now let's look at a histogram. For the data we were working with earlier, the number of missed sticks for blood draws this week. This is a ratio variable. It's numeric in nature. You know the direction and distance of differences between each group. So you know that not only did somebody who missed 3 sticks miss fewer than someone who missed 4, but you know that they missed 1 fewer than somebody who missed 4. You also have a true 0 point here. So it's ratio data. You need to use a histogram. So again, the frequency distribution table informs the frequency distribution graph. We have all of our full range of values in our data set, all of our scores, the full range of scores represented on the x-axis. Now in this case, it is numeric in nature, so you want to have lowest to highest, left to right along the x-axis from 0 to 4. And then the height of each bar corresponds to the frequency of each score. So there are 37 phlebotomists with 0 missed sticks. Find 0 along here, go up to the bar height of 37 that represents the frequency of phlebotomists. And you can see how, again, that table informs this graph. Now, another way that you could display this data that is still accurate would be to use a polygon. So remember connecting the dots, using lines. Polygons are really useful for detecting the shape of a frequency distribution graph, which I'll talk about here in a little bit. Both displays of data are accurate. But if you're asked to place data into a histogram, you better put it in this format, versus if you're asked to put it in a polygon, this would be the format that you would use. But still, the height of the line represents the frequency for that specific score in the data set. And when you create your graphs, make sure that not only do you provide labels for the values in your data set, the frequencies and the scores, but you also label in words what each axis, what those scores represent. Here's another example of ratio data. Remember that grouped frequency distribution table that we did earlier? Well, age is ratio data. So we looked at this and we said, okay, lowest to highest, left to right on my frequency distribution graph on my x-axis. Each category is represented. And then the frequency of each, the bar corresponds to, the height of the bar corresponds to the frequency of each group. How many people were between 10 and 19? Boom. 3 of them, height of the bar goes right up to 3. Now here, as I think I mentioned earlier, your bars touch to represent the upper and lower real limits. Think about it. Age is a continuous variable, and there's probably some people who are between 49 and 50. Maybe you're 49 in 3 days. Well, that represents the upper real limit of 49 and the lower real limit of 50 right here. Bars touch to represent the overlap in the continuous nature of the variable. Just like before, if you're using ratio or interval data, you can put it into a polygon if you like. Again, that helps you detect shape, which I'm going to talk about next. So you can see how these two pictures correspond with one another. Polygon, you're using lines. Histogram, you're using bars. Okay, let's move on to frequency distribution graphs and how that tells you the shape of a distribution. Now, the shape of the distribution is very important when it gets to deciding which measure of central tendency is most appropriate, and you'll be seeing that in the next lecture. But it's also nice to know what the shape of the distribution is just to look at the trends in your data. And here's like a somewhat funny joke. You got a ghost, it's a paranormal distribution. Oh no. Sorry. This normal distribution, by the way, is something we are going to be working with all semester long. So get real cozy with the normal distribution, or the bell curve. So one major characteristic of distributions of data is the shape, and that is revealed by the frequency distribution graph. And the shape of the frequency distribution graph is just created by essentially tracing a line across the tops of a bars in a histogram, or by creating a polygon. Typically, we don't really care too much about the shape of a distribution when we're using bar graphs for nominal data, because remember, the placement of categories along the x-axis is arbitrary, so the shape isn't really meaningful. Just wanted to point that out for you. Okay, so shape can be categorized in terms of modality and symmetry. So when you're talking about symmetry, a symmetrical distribution, basically if you folded the distribution in half, like if you drew a line down the middle of the distribution and folded it in half, if it was symmetrical, the halves would be a mirror image of each other. Then you also have skewed distributions where it's not symmetrical and scores tend to pile up on one side of the distribution or the other. If the scores tend to pile up on the high end or the right side of the distribution, so remember, higher scores are to the right, lower scores are to the left, then you have a negatively skewed distribution. If the scores tend to pile up on the low end or on the left side of the distribution, you have what's called a positively skewed distribution. So in addition to symmetry, modality is another characteristic of frequency distribution graphs, the shape of them. You will get to the mode when you start to look at measures of central tendency, but I'm sure some of you have heard of the mode. It's just the most frequently occurring score. So if you have a unimodal distribution, that means there's only one score which occurs most frequently. If you have a bimodal distribution, then you have 2 scores that occur quite frequently, or you can have several scores that occur very frequently and call it a multimodal distribution. So symmetry and modality. Is it a mirror image? How many peaks do you have, essentially, in your frequency distribution graph? How many, tall points representing a high frequency of scores? So here are some nice pictures for you. This is our normal curve, what we're going to be working with quite a bit this semester. And for the normal curve, if you're thinking about, you've got your variable in order of lowest to highest scores, left to right, and the frequency, most people fall right in the middle. And then you have some extremes on the high end and some extremes on the low end. So most variables in nature, in the population, do fit a normal curve. One example would be personality. So maybe you're looking at extroversion, or how social you are, how much energy you get from social interactions. Well, you have some people that are super extroverted and they need social interaction to keep going. Then you have some people on the other end of the spectrum who are super inward. They are not extroverted at all. They don't get very much energy from interacting with people. They like to be alone. but most people fall somewhere in between. It's like, yeah, I like to interact with people, but I don't need it to survive, per se. Every single day, I don't have to interact to be happy and normal. So that's an example of a normal curve, people falling in the middle. Another type of distribution is rectangular, where there's the same frequency for every single value in the data set. So let's say if there were 5 nurses that had 4 missed sticks, 5 nurses with 3, 5 nurses with 2, 5 nurses with 1, and 5 nurses with 0. You would have a distribution that has this shape. Another silly example would be like number of eyes among everybody in the statistics class. Everybody has 2 eyes, so everybody has the same frequency of eyes. That's a silly example, but there you go. Both of these shapes are symmetrical. If you folded it across down the middle, fold it in half, you would see a mirror image on either side. These are also unimodal. So here you have one score that's clearly more frequent than every other score in the data set. Here, there really is no mode because there's only, all scores are the same, occurring the same amount of times. Now here are a couple of other shapes that are symmetrical. Well, I tried. These aren't perfect, but if you, like for instance, this one, if you folded it in half, it would be a mirror image. This one, if you folded it in half, it looked a little bit better. It would be a mirror image. This one is bimodal. There's 2 peaks in my frequency distribution graph, 2 scores that occur quite frequently. This one's multimodal. There's a bunch of peaks in my graph, a bunch of very frequently occurring scores. Now, these are skewed distributions. They're not symmetrical. They are unimodal, though. You can see that there is a clear winner for which score has the highest frequency. Here's your negative skew. So you've got your tail. This is called a tail. Your tail to the left. So if you're thinking about your data, most people have a really high score, and then you have some outliers over here that have a low score. Negative skew. The bulk of scores pile up on the high end, some scores on the low end. Now, a positive skew is the opposite of that. Most of the scores pile up on the low end of the distribution. Remember, lowest to highest, left to right for your scores here. And then you have some outliers in the high end of the distribution. I don't know if this works for you, but I remember when I was taking this class for the first time, I could not keep my negative and positive skew apart. I could not even remember. So, one way that I think about it, if you tilt your frequency distribution graph over on its side, you just kind of turn it over, starting with like the bottom left corner. If it's a P, you've got a positive skew. If not, you have a negative skew, if it's skewed at all. So I hope that helps you remember. Okay, so that is all I have for you for this lecture, going over the frequency distribution tables and graphs. And the next set of lectures for this chapter will cover some example problems that I encourage you to try on your own, and then you can watch the video covering those answers.